Gaussian concentration, which is a very general result about the, let's say, standard Gaussian distribution. So if you have a Lipschitz function and Lipschitz is respect to the L2 norm, that's the Lipschitz property that we care about here. Then the function f of x, if x is a standard Gaussian vector, is going to concentrate around its mean, and the concentration is sub-Gaussian. And the interesting fact is that there is no dimension in this result. Okay, so it's a dimension-free result, which makes it really powerful. So how much you concentrate, it doesn't depend on the dimension. It just depends on the Lipschitz constant, which is expected. There are a couple of consequences of this. Concentration of the norm and norm squared are an application, but these we could get by different means. Concentration of more interesting functions like the order statistic is a consequence. In this particular one, the maximum is very interesting. So it tells you that the maximum of Gaussian, but I Gaussian random variable is close to the expectation, and you know that expectation grows like it's like bounded by root something like this 2 log n, and so the concentration doesn't depend on anything. So it's like this plus minus all 1, and this can be extended to Gaussian processes. And oftentimes we see the Gaussian processes we care about bounding this because the random quantity here is very close to it. So most often the problem of controlling the maximum of the Gaussian process reduces to just controlling the expectation. So there are a lot of results on more sophisticated Gaussian processes on how to control this. You may see some of them later. But one of the reasons that people focus on this expectation a lot is that the actual random quantity is very close. I should also point out that you might get better bounds than this, or more useful bounds than this. Let's say for other order statistics. The problem with this bound is that the expectation of the order statistic is hard to calculate. And also it is. There are techniques to do this here, to do it for this one, but it might be possible to directly bound that. If you don't try to say that the ignorance statistic is close to the expectation, you just want to bound the size of it. Some other techniques might be useful. Similar to the thing that we did, for example, you could do like control the maximum on this, but you knew that if you don't care. So those techniques can be used to control the order statistics as well. So maybe this could be an exercise or homework problem. If you guys really feel like doing it, I could try to assign. Okay, so one thing that I want to do is to recall some of this discussion, the detour that we took here somewhere. Where did we take the detour? Oh yeah, so we did a rather quick review of matrix norms. I just want to remind you that we had an operator norm, we have 2 operator norms, but we have two operator norms, which is defined like this is the maximum norm of AU, where the norm Q is bounded by 1, and then there are the job like this. There is the Frobenius norm and the Thier norm, and together with the operator norm, these are all examples of key norms. They call it key Chapter norms. Chapter is the name of the guy, I believe. So they all can be written in terms of singular valuation. So singular values of A are non-negative, usually ordered in a different fashion. The Frobenius norm, which norm is the L2 norm of this vector. The PR norm or trace norm is the L1 norm, and the operator norm is the norm. Okay, so these are some of the interesting facts about matrix norms. And then all these norms that are defined in terms of the singular values are inherently very easy to see, because if you multiply either new matrices or orthogonal matrices, yeah, if you do this transformation with U and V or orthogonal, this is not going to change the singular values. You can just read off, if you write down this u of this, you can read out this given this. This gets multiplied by whatever is here. There, so you just modify the singular left and right singular vectors, but you don't change the singularity. So all of these are unitary invariant, and you can see that, for example, among them, the operator norm is the smallest. It is the smallest of these Chatham norm, and probably the smallest unitary invariant norm, or at least within this class. And this is the largest. This is okay. So before we call this, okay. So now go back. Let's go back. So the analog of the concentration order statistics is the concentration of singular value. If I have a matrix, if you look at the vector of singular values, usually your orders are like that. Let's say here I'm assuming that the rank is K, so the rest are 0. Sometimes you don't show them, but you can go all the way to, let's say, the minimum of M and D. There is a theorem, which is called Wales theorem. Tells you something about the perturbation of the singular values, or perturbation of eigenvalues for the symmetric matrices. So if you have two matrices, and if you look at the difference of the singular values, it's bounded by the operator norm of the difference. Another way of like writing this is usually that I have, for example, x here, and then y is x plus delta. So you perturb x a little bit, you want to see what happens to the singular values. And this is saying that the difference of the singular value is bounded by the operator norm. And the operator norm, as we discussed shortly before this, is bounded by the Frobenius norm. Okay, so Frobenius norm is bigger because this is the L2 norm of the singular value of delta. This is the so now if you look at this in broadly, if you view the matrix as just a giant vector, think of a matrix as a collection of entries. You can order them into a big vector. So think of X as, sometimes you look at it as like vec X if you want. This is in R and D. So if you have a matrix, you just go pick these entries and then concatenate these guys, put them here, and then the next column put it down there. So you just get a giant vector. So this singular value is a function of that giant vector in a complicated fashion. And so it's a function, we can think of it as a function of that vector. As a function of that vector, this is going to be the outcome of the difference of those vectors. So the Frobenius normal matrix is just a, we want to write it xf with the L2 norm of vec x if you want. Okay, so in terms of the vec x, you can think of it in terms of the vec x. This is a function of the vector algebra x. And this inequality shows that that function is vectors with respect to the L2 norm. Okay, so this Frobenius norm is just the L2 norm for vector. What it's saying is that this map is one Lipschitz in the right norm that we care about for Gaussians. So if that's the case, then if x is a random matrix with entries that are either 0, 0, 1. This is basically a giant IAD for like the standard Gaussian vector. Then the singular I is X. If singular I finds simplification is Gaussian because it's one dimension, the constant here is 1. So this inequality is very useful. We want to write it for because sigma 1 is the operator norm. This just immediately gives you that the operator norm concentrates. So the probability that the operator norm of X minus its expectation is bounded or is bigger than T is less than or equal to 2 to the negative delta squared over 2. And the techniques for bounding this, we'll see a more general result bounding something like this for Gaussian matrices. But there are techniques for bounding. So if you write this as supremum of, let's say, X, U, L2 norm, I can then write this as supremum V transpose XU U L2 less than 1, V L2 less than 1. So why can I do this? Yeah, so right. So this is saying, for example, that L2 norm is supremum V transpose A, let's say. So I'm just replacing this with a variational version, which is this. And let's say if you separate separately, like optimize first over U, you justify it for yourself. And this we can think of as the expectation of, let's say, a Gaussian process, supremum of a Gaussian process, sup. I can also drop the absolute value. There's no absolute value here. It's just sup yt, t in t, where yt is v transpose xu, and t is just this index. So if it's a process index for two vectors, and the technique for bounding this is like maximal regression process, as I mentioned, the expectation. They're the results that we can use, particular Gaussian comparison inequalities. So you can compare this to the supremum of another Gaussian process, which is simpler, and then that we might see some example of this later. But what I'm saying is that there are good techniques for controlling these things, and this is an example of that. And so we can control this very nicely, and this tells you the operator over Gaussian, and the matrix is very close to that. So for example, what we can end up showing is something like this guy is bounded by root n plus root d. Something like that. The result, if it's n by d, then you'd get something like that. We'll prove something like this up to a constant later, but for the Gaussian, you can get a very sharp bound with the constant 1 here. In any case, what I'm saying is that this is very useful to put controlling the operator over the Gaussian. So you have this result to control the operator, the expectation of the operator by the technique, and then this tells you that this is very close to that. I'm going to come back to this. Just keep this in mind. We're going to see this version or characterization of the operator quite often. So that's called variational characterization. You're expressing the operator as an optimization problem. That's why it's called variational. Question?
Sounds good. Okay, I think we have enough concentration for now. So now let's move on to some other topic, which is basically, let's say, one of the main problems that we're going to look at. This is basically the motivation of the high-dimensional statistics literature, let's say, or the cornerstone, or why the book was written, or like everything else follows more or less from this. Linear regression in high dimensions. So if you recall, how many people have seen linear regression? Okay, so what is linear regression? Maybe you guys can talk instead of me. No, just like talk a little bit about what is the problem of linear regression. Yeah. Yeah. Okay. Yeah, that's like the Gaussian solution or Gauss's solution to regression. But let's say as a model, what kind of model is it? It's like, let's say I have, so you can think of it as a vector, but you can also think of it as I have observations, xi, yi. This is like the general setting that you encounter in statistics and machine learning. So you want to predict yi given x, like, or y given x, right?
Predict the model that maps xi to y.
Yeah, so we want to build a model that maps basically, yeah. So what is the model that the linear regression assumes? Can you say that again? Let's say beta, xi transpose beta. Yeah, so that's one way of doing it. So let's say these are coming from a distribution. So I can think of it like if there's a generic pair that's generated from the same distribution, and what you assume you assume something about the conditional expectation of y given x, which is that this is linear. Then I can write y as, this is one way of viewing it. I can write y as this minus or plus y minus the expectation of y given x, right? So this is beta, this is going to be xi transpose beta or beta transpose x, yeah. And I'm going to call this epsilon. This is some error. In this formulation, it's fairly general. Epsilon is going to be uncorrelated with this. If you recall the projection model, and this will be 0 means. But usually for this course, we often assume that this is actually also independent of x. Okay, so it's just an independent piece of noise. In general, it doesn't have to be independent of x. For example, you have a variance that depends on x. It's just a remainder of this projection. But what we're going to assume is that, let's say y is x transpose beta plus epsilon. Epsilon is like independent of x. And usually you assume it to have a certain distribution. For example, we could have a normal distribution, right? And then these guys are from the same model. So these would have like xi transpose beta plus epsilon I. And then epsilon i's are, let's say, independent of xi. And epsilon i's are, let's say, for example, standard normal. Not standard, but this is the simplest version of the model. And then oftentimes in this course, we're going to assume that the condition on xi's or xi's are fixed. So the only randomness is in epsilon I. Okay, so basically a linear model is sort of imposing a linear constraint on the relation. It's model the relation as a linear function. So this is a linear function of x plus some more. If I change the nature of this function, that would be different. So non-parametric, let's say different some other model. So a linear model or linear regression model assumes a linear form where the relation between x and y in expectation is linear. Okay, yeah. That's a good point. Did I not upload it? Yeah, I can do this. Okay, so if you write this model in matrix form, you would get, okay, I should have mentioned theta. You were right. This was, it seems like it was theta, theta, let's say theta star, true theta. Theta star. So I can write this as, in a vector matrix form. If you form this design matrix, the rows are x1 to xn transpose, that is n by d. And then you can see if I multiply by theta star, basically I would form x1 transpose theta star, x2 transpose theta star up to xn transpose theta star. Right, and then y would be y, and this one would be, this is just y1 up to yn. And you can see if I set this equal to this guy, and then this is like w1 up to wn. So you get those equations that we had here. And wi, and we're going to assume that this xi is unknown. Did I miss it? So that's what fixed design setting. Xi unknown, and unknown parameter wi is random and unknown. Yi is random and observed. No. Okay. So as Kyle pointed out, the classical approach to solving this is to, you want to estimate theta star, so you would form the least squares estimate. We talked about it in the first lecture. So argument y minus x theta, or theta, we have OLS x theta squared theta in r to the d. This turns out to be, for example, the MLE as well, if you're under the Gaussian assumption. So under the Gaussian assumption, this would be normal between 0 and sigma squared ID. That's how the result that we talked about, both of them are valid for sub-Gaussian noise as well. So this is the MLE under the Gaussian assumption. And this turns out to have a well-known solution in cases where, so if x is in R to n by d, and let's say n is bigger than d and x is full rank, then there is a unique solution. This has good properties. Okay. It's the best unbiased estimate, best unbiased linear estimator. So minimizes the variance among unbiased estimators in some sense, and so on. And then the issue that we talked about is that this is all good if n is bigger than d, but oftentimes in high-dimensional statistics, d is much bigger than n, so this problem does not have any, it doesn't have a unique solution, and even if you pick one of the solutions, you're going to perfectly fit y. So y minus x theta can be made, you can make it 0, such that y is equal to x theta. And that's not generally good. So you don't expect something that reproduces y exactly to perform really well later, because part of this is noise and you don't want to be fitting to noise. So, okay. So anyone remembers what was the solution or some of the solutions that we talked about? Yeah, okay, great. So you should add some constraints of theta, and the main one that we care about in this course is sparsity. So if, for example, if we assume, so let's define score theta star, which is we use for support and also S theta star for short. This is the set of all non-zero elements, or the indices of non-zero elements of theta star. So the hardest part of the concept imposes the bound on the cardinality of the set, how many elements it has. So let's say the cardinality is S, we're going to see that S is much less than implicitly. So the results that we're going to talk about hold for all S and B and N, more or less, but they're really useful if S is much less than. There is another kind of a sparsity assumption, which is a weaker notion. So you might think that this might be too restrictive to assume that all thetas are exactly zero. Although traditionally, statisticians do assume that like they test for the coefficient to be zero, so it's not something uncommon. But if you want to allow, like relax assumption, allow more flexibility, you can say the entry is not zero, but a lot of them have to be small. And the way to measure it is one way is why this so-called LQ ball constraint. So if you recall, the LP norm of a vector, or if you want the LQ norm, is defined to be something like this. You take the absolute value of the elements to the power q, sum them, and then form the power of over q. So if q is bigger than 1 or bigger than or equal to 1, this is a norm. Norm for but if q is less than 1, this is no longer a norm. But this guy, I forgot what it's called, quasi-norm or something. It satisfies certain properties. It satisfies something like a triangular coordinated constant. And in particular, this can be used as a measure of sparsity. So if the vector is dense, this is usually large. And if this is small, usually there are a lot of entries that are zero, they're close to zero. To see this, here's from the book. I think the picture from the book showing the unit ball of these norms, the LP or Q norms, for different values of Q. So this is, I believe, Q equal to 1. E is Q equal to 3 over 4. And C is Q equal 1/2. Okay, so you see it gets pointier as Q gets close to 0. Eventually, it just like hugs the axis. So, so what it is saying is that it's easier to actually do it in 2 dimensions. So this would be like a 2-dimensional version of the L1 norm. This is the unit ball of the L1 norm. This is the, yeah, it's hard to plot, but this is the unit ball of the other guy. And this is the unit ball of the other guy. Okay. So what it's saying is that because this is the unit ball, anything inside has norm less than or equal to 1, or yeah, I think this is still, I'm going to call it norm, that it's not norm. You understand what I mean? This quantity less than or equal to 1. Anything outside has norm bigger than or equal to 1. So what it is saying is that things that are here, for example, are going to be outside this unit ball. So this is not really that sparse. But things, for example, that are here or here are quite sparse. They're there. If you increase it, eventually you capture this point. So and then in L1, so this point, for example, is inside. Okay. This is still a bigger than let's say L2. L2 would be like this, so it's even bigger. And you can see as you decrease the Q, the vectors that are in the LQ, the unit LQ ball get sparser and sparser. Things that are dense, for example, have to be like very small. Yeah, all the edges have to be very small. Okay. And that's the sort of intuition why this is a good measure of sparsity. And you can see that this is a convex set, the L1 unit ball, and also this one, but none of these are convex. So the fact that these are not convex means that the function is not a norm. Okay, it's a norm for only if it's convex. What else? Any questions about this? There's another version which is called the weak LQ, which just controls the decay of the ordered values of these entries of theta, the absolute values of entries. But let's not worry about that at the moment. This is good enough. And okay, so this is the assumption that we're going to make. We're going to start with hard sparsity. So now, so what do you guys think we can do? Again, if you recall, we talked about this. Assume that I have this hard sparsity. What can I do? How can I modify this to take advantage of this assumption? Right, we don't know. Yeah, that's the thing. So we don't know the pattern. If we knew the pattern, basically the problem reduces to just yes, yeah. So we don't know the pattern. That's a good point. So all we know is that the number of elements is S, which hopefully is much less than P. But there's no assumption about the locations. So how should we? We know D, right? You're right. We let's say we might not know S, but let's say even if I give you S, how should you go about it? Let's say I give you S as well.
Can we solve the minimization problem? Like, I don't know, but like minimizing an affine combination of X values over something.
A fine combination of X values.
Like C transpose X.
But
We're
X-
trying to minimize C transpose X, subject to
X.
C,
X is a matrix though, right? So what do you mean by this? This is going to be a vector.
I'm sorry, I was thinking about one single element, right? So it could be a matrix, sorry, like minimizing so minimizing y minus norm of y minus.
So why not just do this? So
Yeah,
this is, yeah, this is okay. So we can still minimize this. Subject to what?
That's the same.
Okay, we can do something like this. Is this gonna work? That's what you want to say. Okay. Is this okay?
Yeah, but I think it's the same problem. This is how it solve the high dimensional problem.
There are two problems. One, whether you can like computationally solve it. The other one is whether statistically it makes sense. This statistically makes sense, right? So we have solved, if you agree, I like accept my word for it. If you solve this, you've solved the statistical problem. It might be like infeasible to do it in practice, but this has a it could have a well-defined solution, and it could be consistent for the two data. This is the natural thing to do. The first thing that you would like come up with if you have the constraint. If I know that, so okay, I didn't mention that this is sometimes called the L0. So the cardinality, this is sometimes written as the L0 norm, although it's not the norm. You can imagine it's the limit of this. As it goes to 0, the only things that are it's hard to see from this, but when it goes to 0, basically the L2 norm converges to the number of non-zero elements. So if you have a constraint, the easiest thing to do is just to impose it on the. If you have an optimization problem, you have a constraint on the parameter, just impose it as a constraint and try to solve it. So that's exactly what people propose. The other approach is like, so this is like the noiseless version. Suppose you have the noiseless version. This is the first thing that people were looking at. And then when I try to minimize this, I know that I can get this to go to 0 perfectly. So I'm gonna basically impose it as a constraint. So I'm gonna look among the solutions. I know that there is no noise, so I'm gonna look at the solutions. Among the solutions of what I collect data, and then I'm trying to find the smallest solution. This is similar to this. It's like the you think about it, it's the dual or the Lagrangian version of it in the noiseless case. This is a little bit better because you're not imposing. You don't need to know the S. Okay. Also, like it finds the sparsest, which is if you have like two solutions, both have L0 norm less than S, you probably want the one that is the sparsest. So this is the thing that people wanted to solve. This is called basis per suit, if I recall correctly. The issue, as you mentioned, is that if you want to solve this, how do you solve this? Let's say you want to solve it. Like the strategy to solve this.
But this L0 norm doesn't actually depend on the actual values of all that stuff.
Yeah.
We can assume that we can assume all to be 1.
All of the
Like S problems are going to be 1, and then
S, yeah, okay. So
which of those S
okay, sounds good. Yeah. So what you can do is like assume. What I can do is something like that. Minimize first over all the thetas, such that theta naught is equal to S, and then minimize over S. And what this is saying is, you're gonna start from the smallest S. Let's say S is 0, which is just a 0 vector. The 0 vector is not gonna solve this usually, and that's why it's 0. So you go to S equal to 1. Among all the vectors that have exactly one non-zero element, you have to solve basically problems, right? So I would assume that the first element is non-zero. So you plug this in, you get a linear problem. You can try to solve it. This one, 0 elsewhere, and so on. You're trying to solve all these D problems. If there is a solution, good, we're done. Maybe there are two solutions, you just output them. If there are no solutions here, then you go one step further and S equal to 2. Now I'm going to have to worry about things that look like this: theta 1, theta 2, 0, 0, theta 1, theta 3, 0, 0. Okay. So I'm going to take all the vectors that have two non-zero elements. each one of them gives you a linear system you can solve. If there is one there, then you're done. If not, you choose S. And so the like S, D choose 1, D choose 2 here, D choose 3. So you keep going. And if there's a linear sparse solution, you might be able to do it. You might be able to find it. Let's say S equal 3 works. This is like e to the 3. The complexity is still manageable. But then as your S increases, problem becomes harder and harder, like computation. But mathematically, you can solve it. One question is whether the solution is unique. That's one of the things that people worried about. Is the solution going to be unique? Can we impose a condition that the solution is unique?
There might be multiple sparsities that give the same result because we're interested in the most sparse case. I think for a specific S.
For a specific S, it would be, it's not necessary down to do we want it to be, right? But let's say for different S's, you don't have to worry because we're going to take the S that's the smallest. Right? So the smallest S that works for this.
So the given S, if S is smaller than or equal to N, and we'll have a full rank. Hopefully we'll have a full rank.
Yeah, so that's the hope. Okay, yeah, so we have to impose that assumption. So let's say X restricted to a subset S of size S has full rank. Like these guys as basically S varies. So XS is full rank. Full rank as S varies among all subsets. Sets of N of size D. D of size S. So this is choosing this notation. Sometimes I'm going to use it. What it's saying is that I'm going to choose the sub matrix of X on columns indexed by S. Okay, because we don't know which one of these subsets is going to be the support that we can impose this assumption that X of S is full rank for all these subsets. If that's the case, then the SSR solution has to be unique. We need some sort of assumption like this. Okay.
Still need the assumption that S is smaller or equal to N, right?
So this imposes that assumption. So if S is bigger than N, this cannot happen, right? So these matrices can only be full rank if S is less than N. Right, so this assumption includes what you, yes, never mind. So there's assumption under assumption if I solve this, let's say this S is the true S. We know that basically any solution that was sparsity S or below is going to be unique. And we know that there is a solution, theta star satisfies this, so we have to be able to recover it. So theta star in this sparse and satisfy this. Under this assumption, no other S sparse or below S sparse solution can exist. And so this procedure, if you start from below, is guaranteed to find S theta star. So you can recover theta star exactly under the assumption. Okay. Makes sense. Okay, but then people, as you pointed out, they noticed or they knew that this is not feasible. So what we need kicked all of this into like here was that people realized that we can replace this to be L1 and this is higher than 10x. This is convex problem. And it turns out that the solution of this, under some conditions, still is going to be theta star. So you can recover the theta star exactly. If you minimize this, like this is not obvious, this is obvious. And the advantage is that it's a convex problem. It can be reduced to a linear program, and it can be solved very fast. The other point is that, unlike many optimization problems, convex D sub-convex problem, you can guarantee that you find the global minimum. There could be multiple global minimum because the function is not strictly convex, but you can find all of the global minimum, or at least one global minimum. So this, like, empirically was sort of observed, and then people try to prove it. Okay, so how can you show or find conditions under which the solution of this, just like a condition like this that we have for this guy, then you have a condition for this that guarantees that if the system equation has a sparse solution, sufficiently a sparse solution, take the star testing sufficiently small, then I would be able to uniquely identify. Okay. So that's more or less the start of this whole business. So any idea? Have people seen how to? Is the problem clear? So let's understand the noises problem first. Then we can sort of understand better what happens in the noisy case. Yeah, it's a little tricky. So I'm going to give you the answer, and I'll try to. If you haven't seen it, it's not obvious. The condition is not obvious. So let's define the set. Instead of all delta such that delta is complement of one mode delta is complement less than or equal to the other mode of delta s. So delta here is a vector in RD. And the notation that I'm using here is I'm going to partition it into two pieces, S and S complement. And delta S would be this part. Delta S is this. That's delta S. And this is delta S complement. Okay, these are subvectors. So you can imagine S being a small subset, S complement is a big subset. So you want the L1 of the big part to be bounded by the L1 of the small part. So the set of these vectors define a set in RD. If you plot it, let's say if I have just, it's hard to visualize, but in R2, let's say S is 1, then S complement would be 2. So what this is saying is that I'm looking at all the vectors, delta 1, delta 2 is such that the L2, sorry, absolute value of delta 2 is less than or equal to absolute value of delta 1. And if you plot this, this is delta 1, this is delta 2. It would be something like say this part. This is going to be this plus this. Okay. The part for which delta 2 other way. Yeah, sorry. Let's change the other way because I think that's the picture that I have in mind. So let's change these two. 2, 1, So 1 less than 2. So it's a cone, but it's not a convex cone. It's a cone in the sense that if you have a ray, like a line passing through the origin, if one of the points is on this, then the entire line is there. But it's not convex. You can see, like, if I join these 2 points, they're not going to be connected. So having defined this cone, we have this result. If theta star is an RD and the support is an S, or let's say for any theta star in RD support in S, the basis for two formula, minimization basically, applied to the data, which is y equal x theta star. So basically what this is saying is that if I solve the problem, minimize theta 1 subject to x theta star being equal to x theta. So this is y. This is what I observe. If I solve this problem has a unique solution, which is going to be theta star. That's one statement. The other statement is that this set intersection with the kernel of x basically is trivial. The only vector that's in there is the 0 vector. So these two properties are equivalent. So you can recover all S bars, let's say, or capital S bars in the stars by solving this. This is basically equivalent to recovering all possible theta star S, or theta star supported in S. Kernel of X, what do we mean by kernel of X? It's just the null space. Kernel of X is just X, the set of all theta such that X theta is equal to 0. So it's a subset of RD. Okay, if you recall, this kernel is problematic because if I add anything from the kernel to theta, it's going to satisfy these linear constraints. So if I just add these linear constraints, this part is not identifiable. So if I have solutions, add it to anything in the kernel. So what this is saying is that this kernel, which is the non-identifiable part of theta in a sense, or encode that, when intersected with this cone, does not have any like non-trivial vectors. So in this picture, for example, the kernel of X, because it's a linear subspace of R2, for example, if the kernel of X is this, then this is satisfied. If the kernel of X is this, then this is violated. Okay. So there is this region where the kernel can pass through, and that's where this condition is satisfied. Is this statement sort of clear? So this is a very nice result because this is some sort of a condition on the X matrix. Similar to the one that we had, right? So this was a condition on the X matrix and also like the support that we care about. This is similar, a condition like X and the support that we care about. So how do we prove this? Yeah. The what? So this is they're the same sort of, there is one part of this here. This is saying this holds can only this. Right? So what it's saying is that the property that you can recover any data star supported defense by solving this is equivalent to this condition. Okay. For obvious reasons, this is called restricted null space property. So this is the null space, and this is a restricted null space. So this is the saying the restricted null space of X is trivial. Okay, so how do we prove it? The proof is very interesting, at least the one that I have here. It sort of is in the book. It's a very geometric proof. So let's define the tangent cone to the L1 ball at theta star. So at theta star, if you think about the like any function, let's say, if I evaluate this function, let's say at theta star, and then I perturb theta star in a given direction, like delta, by a little bit. So P is positive, delta is the direction. If I look at this and compare it to this, basically the directions in which this is going to be less than or equal to f theta star directions that I can descend on the function. Okay. So I can decrease the function in those directions. Direction. So let's say fix the direction. There is a t such that this holds, then if I move in that direction without a step size, I can at least I don't increase the function and hopefully decrease it. So these are called descent directions, and this tangent cone is defined as a set of directions that are the descent directions of L1 at theta star. Okay, so at theta star, look at all the possible deltas for which there is some t such that this is less than theta star. If delta is not in there, it means that if I go in the direction of delta, for all values of t, I'm going to increase. So these are the potential directions that can violate like the property they want. So I'm going to take a star, okay, that's our solution to the problem. Seems fine. Okay, so the right, so we have x theta, let's say equal x theta star, and sorry, that's not what I say. So if you look at this linear system, theta star is definitely a solution. Okay, and all the other solutions of this can be written as theta star plus the kernel of x. Okay, so the set like theta belong, like theta such that this is equivalent to theta star plus the kernel of x. What this means is that the set that's constructed by adding theta stars to the generic element of this. Okay, so that's the sort of feasible region of the problem. That's what I'm trying to say is this. This is x theta star. This can be written. The feasible region can be written as a shifted version of the kernel. And if you look at the kernel itself, because this is a feasible solution, if theta basically belongs to this, it's feasible. So theta minus theta star, which is this delta, is a feasible direction. Okay, all the possible solutions can be obtained by adding these feasible directions to theta star. So I'm going to focus on these feasible directions, and what I want is that none of these feasible directions have to be a descent direction. That's it's equivalent sort of to recovery, right? So if there is a feasible direction that is in this cone, I would have I can find t such that I can move in this direction, and the t is as good as this. So there's going to be at least another solution. I might actually keep this. So the condition of recovery, like unique recovery of theta star, if I minimize the L1 norm, is that none of these feasible directions is so hence theta star is the unique minimizer if only if the intersection of, but this is like the opposite. There is a minimizer other than theta star if the intersection is not empty, or it's unique if it's empty. So far, so good. That makes sense. Okay, so the only thing that you have to not do, because the condition that I have is that I want to have it for all theta stars that have a certain support. So I want this to basically the opposite of this, which is I want this to hold. If this holds, then for that particular theta star, we're going to keep the unique. I want this to hold for all possible theta stars that have a support in S. So basically, I want to show that if I get the union for all of these, the union does not potentially take care of as well. If you look at the union, if I can show that this union is actually in the CS, then we're done. So that's basically the idea. So you would then have CS intersect with the kernel of X is union something like CS theta star intersect with the kernel of X for all theta stars such that support of theta star is in S. So this being 0 means that all of these are 0. So I can recover all of them. If this is non-zero, then there's at least one that I cannot immediately recover. So this condition is equivalent to and only if I can recover all theta stars that are supported in S. So the only thing that we have to show is something like that. So let me show you the geometric picture first. So that's the L1 ball. This is the setting that we have. This is 2, this compound is 1. This is the S. So let's see the tangent. So the tangent, so there are, let's say, all possible theta stars are, in this case, are these two guys. So I want all the theta stars that are supported on an S, okay, and except for the basically. So basically anything on this line, right? Anything on this line would be a theta star that is supported on S. So if theta star is inside here, the tangent cone would be trivial. I'm going to maybe come back and ask you guys. The interesting points are these points that are at the boundary. These are these 2 points. So what would the tangent cone here look like? So everything in the L1 ball is of unit L1 norm. Anything outside has bigger norm. So what directions can I move from this point such that the L1 norm decreases as to the set of descent directions? So I can move in this direction or this direction or this direction. I can't move in this direction, for example. Okay, so you can see the set of all possible directions would be like this. Okay, that's this thing that I wrote here or drawn here. This is like the cone tangent cone associated with that. It's the set of descent directions. At that point, for this point, you can see it's just this one. What this is saying is that if I, and then these are centered at these points. So if I basically take the union of these, I'm just going to basically join these. These are going to be the origin of these points, right? So this is delta equals 0. So this moves to this part. This guy moves to this part. The union would give you this picture. So that's the union of these two. And that's the CS. So if the kernel doesn't pass through this point, then sorry, doesn't really pass through this point, then I just have the property that I want. This is just to show you how this is constructed from those. What about if theta star is in here? What is the tangent cone in that case? So I'm talking about this. So what are the set of descent directions? If I'm at this point.
It would be like smaller, the same shape but smaller.
It's a little bit trickier. So let's say this direction, right? What this is saying is that if I take any, sorry?
As long as it's parallel to those lines.
Parallel to those lines. Okay, so maybe something like that. Okay, so how about this? Why can I not have something like this? Sorry? Right, yeah, the point is, this is like the cone that sort of, if you look at the L1 ball here, that passes through this point, anything that just is not parallel to this is going to be outside. Right, so at these points is also going to be, yeah, as you mentioned, cone is going to be like this. So there are just two shapes for it, either this or this in this case. Okay, so when you take the union, basically you take the union of all these, a bunch of these and a bunch of these, you get that. Okay. Correct. It's not as tricky, but okay. So the formal proof. Here's the formal proof. So I've defined this quantity. T1 theta star is the subset of this where T is equal to 1. You can argue without loss of generality that it's enough to work with this because I can rescale delta. As I pointed out, so you can show that this is a cone. If delta is in there, then any multiple delta is in there that is defined. So I can just fix T and worry about that case, T equal to 1. Then if delta is in this means that theta star plus delta, sorry, finish now. This is less than or equal to this, right? I'm going to break it into two pieces. I get theta star as complement, which is 0, plus delta as complement, plus theta star s plus delta s 1. This is 0, 0. And I can rearrange. So I've kept this part here, move this to the other side. So I get this. And then if you take the So delta is in this if and only if this holds, and it's gonna hold if like
delta is going to be in one of these lines. If there is a theta star such that this holds, the supremum will be the stars. Yes, so this is bigger than this. If the supremum is bigger than this, then this means that the rate of theta stars for the digits, such that this holds and that delta will be there. So the condition that basically delta belongs to this is equivalent to this, and if you take the supremum here as well, this is true, and you can also see that this is also
exact. So if you don't want to argue if and only if, it's a little bit easier, but this is if and only. So
delta is this union and only this holds. Actually, if you get one of them and only this holds, in the union. And so this just shows the union is actually
characteristics in form. Okay. Any questions? Okay. Thank you, guys. This is the start of the chapter. We're going to come back next time and talk about more easier conditions of this.